Okay, here we go. Last section of chapter 1, we're going to talk about inverse functions. You have talked about this before in Algebra 2, okay? Inverse functions. Here's your notation, f with a -1 as a superscript, okay? This means f inverse. Okay, I have another one of these fun pictures here. The next slide will talk about the definition of an inverse function. Okay, but what we need to understand is that when we go from a function to its inverse, the domain and range are going to switch. So the domain of f becomes the range of its inverse. The range of f becomes the domain of its inverse. Okay. So our definition of an inverse is this. We're going to have two functions, f and g. If f composed of g is x and g composed with f is x, then f and g are inverses. So on number 33, when we composed f with g and when we composed g with f, we got x for our answers. We proved in number 33, without you even knowing it, that those two functions were inverses of each other. Now it does say for every domain. Okay, we'll talk about what happens, why the domain is specific. Okay. When we do this algebraically, there are a couple of times where we have to restrict a domain, so we still have a function when we make it an inverse. Okay, but we'll worry about that in a little bit. Okay. So, like I said on the first slide, our notation for an inverse is f with that -1 superscript. Okay. So if you are ever asked to show algebraically that two functions are inverses of each other, you would have to show that each composite is equal to x. Okay. So this is the same thing as I have written up top. Instead of g, I made it f inverse. Okay. So if you want to write that down, you can. Not a big deal. Okay. But make sure you are comfortable with that notation. You've seen it before, correct? Yes? Still remember? Okay. Well, now you know. I honestly, I can't remember. I think so. I think you've seen it. Yeah, it's probably been about a year, right? Okay, now let's see if you remember this. Graphically, how can we tell, or how can we find an inverse of a function graphically? There is a special property that a graph has with its inverse. Does anybody remember that? Okay, well, first of all, when that very first slide we talked about the domain becomes the range of the inverse. the range becomes the domain of the inverse. So you maybe remember from Algebra 2, if you had a graph, what would you do with all of the coordinates? If the domain became the range and vice versa, to find the inverse, you switched all of your coordinates. Okay, x, y becomes y, x. So if you have the coordinate 1, 2, it becomes the coordinate 2, 1 on the inverse. Okay, does that ring a bell to some of you? Okay. All right, so we're going to look at this graph right here. Okay, so here's my graph. Any coordinate that I have, the x and y get switched. The domain and range, they switch. So this coordinate is 0, 0. What does it become on my inverse? Okay, 1, 1 becomes, okay. That's not very exciting. How about negative 1, 1? 1, negative 1. Here we have 2, 4. And here we have negative 2, 4. Okay, so this is what it's going to look like. Okay, yes?
That's not a function.
It is not a function. That is true. Okay, not all, okay, it takes a special kind of function to have an inverse that is also a function. Okay, and we're going to talk about that here in like 2 seconds. But I want you to notice there's a reflection going on here. From our original graph to our inverse graph, there's a reflection about what?
The origin.
Not the origin. Yes. Okay. The inverse is a reflection about the line y equals x. Here's our line y equals x. Because those x and y values are switching, okay, we have that reflection about y equals x. Okay, so this red graph is not a function, right? But the blue graph is, correct? Okay, when a function and its inverse, okay, if we have a function whose inverse is a function, that is called a one-to-one function. Okay, we call that one-to-one. Okay, its inverse is a function as well. Okay, so not all graphs are going to have an inverse. The only way that I would be able to say that a quadratic, like we have up here, has an inverse would be to restrict the domain. Okay? Now, we have what's called the vertical line test to see whether a graph is a function, correct? Do you remember talking about the horizontal line test at all? No? Okay. I don't know. I don't know if your teacher may have mentioned it in Algebra 2. Maybe. Okay? The horizontal line test. What do you think that would test for? If I draw a horizontal line, how many times does it hit the blue graph? Twice. Okay? Since it hits more than once, it means our inverse is not going to be a function. The horizontal line test tells you if the inverse will be a function. Okay? So if it meets If the graph passes the vertical and the horizontal line test, your inverse is a function. Okay. And it's kind of some vocabulary background. Biggest thing you need to be able to do is create the inverse. Okay. That is how we do it graphically. Let's talk about how we do it algebraically. Now, how did we do it graphically? We did what with our coordinates? We switched x and y. That's what we do algebraically. Oh, I actually had a slide for this. Okay, cool. Well, we talked about that. All right, so algebraically, we are doing the same thing. We are switching x and y. So my advice to you first, it's going to be in function notation. You know f of x means y, so go ahead and change it to y. All right? Then you're going to physically switch x and y. And then since we want it in function notation, we're going to go ahead and solve for y. Okay, so change f of x to y, switch x and y, solve for y, and then change it back to the function notation, but with the inverse symbol. Okay, now I have verify. If I ever ask you to verify, what do I mean? Okay, how do you algebraically verify that two functions are inverses of each other? First thing we talked about. Okay, to verify, you would show that the composites both equal x. Okay, so if it ever asks you to verify, that is what it means. Show that G composed with F and F composed with G both equal x. Okay. All right, so let's do an example. But this isn't the example I want to do. I change my mind sometimes. That's the example that I want to do. Okay. Okay. What is the domain of this function? Everything besides -2. Okay? Because that is where what's going on at -2 graphically? We have an asymptote, right? Now, how do we find a range? Okay, a rational function has a vertical asymptote and it has a horizontal asymptote. Okay, so our range is everywhere except that horizontal asymptote. Do you remember where the horizontal asymptote is for this graph? No, that would give you an intercept. Okay, you had two rules. You had a rule about what these were right here. If the bottom had a greater degree, your horizontal asymptote was at 0. If they had the same degree, your horizontal asymptote was at the ratio. So since you have 1/1, your horizontal asymptote is at y equals 1. Okay, so your range is everything but 1. If you have the same degree, numerator and denominator, your horizontal asymptote is the coefficients ratio. Okay. All right, so let's worry about the inverse. First thing, change f of x to y. Okay? Then to find the inverse, no matter what we do, algebraically, graphically, what do we do with x and y? And now we have to solve for y. Ideas. How do I solve for y?
You multiply by y plus 2.
Okay, you want to multiply both sides by y plus 2?
Just the x though.
That'd be okay.
It's still work.
It's okay. Yeah. So Joey says multiply by y plus 2. Okay. So we have xy plus 2x equals y minus 3. Now how do we solve for y? We can't ever divide by a variable because we don't know if it's 0, and we can't divide by 0. So we can't divide by a variable. Do we have more than one y? Yes. Would it be a good idea that we get them together? Probably want them together on the same side at least, right? So what I'm going to do, I'm going to keep xy here, and I'm going to move this y over. So I'm going to subtract y. And then I'm going to move this 2x to the other side since it doesn't have a y value. Okay. Now what can I do with that left side? Can't divide the x. Can't divide by a variable. Look at the left side. What do both of those terms have? They both have a y, which means it can be factored out. We can factor out a y. Okay. Now, how do we solve for y? Mm-hmm. Okay, and then we're going to put it in inverse and function notation. Okay, now what did I tell you about the domain and range from a function to its inverse? The domain and range from a function to its inverse, what happens? They switch. So since the domain was everything but -2, our range becomes everything but -2. Since our range on the original was everything but 1, that's what our domain becomes. Okay? Well, let's compare these to our function. We have a rational function, okay, which makes sense. The inverse should probably be rational. Okay? What makes the denominator 0? 1. So our domain, everything but 1. Okay? Where would our horizontal asymptote be? -2. So our range is everything but -2. Okay, so those should match up. Okay? Yes?
What happens when, say, like you're an x squared on top and x on bottom? How would you do your range?
We will talk about that in a later chapter. Okay? Because that's when we get a slant asymptote. Okay, we have a few minutes. I want to do one more example that will be quick. Okay. I want to look at this problem right here. Okay. What do we have here? square root function, right? Okay, a square root function that's been shifted. Okay. Okay, quick, easy graph. Okay, let's go ahead and find the inverse, and then we're going to talk about the domain and range. Okay, so our inverse. We need to do what first? Switch x and y. Now what? We need to square it. Okay, we need to solve for y, don't we? So if I want to isolate y, let's get rid of that square root so we can square both sides. Then okay. Now, we would like to say that the domain of this is what? Oh, reals. It is not. Why, Mrs. Hillman? Let's go back to our function. What's the domain of this function? Where does the domain start? Because it doesn't go on forever in this direction. Where does the domain begin? -2, and then it keeps going, right? Okay. And what about our range? Where does our range begin? 0. And then it grows, right? Okay. Graphically, when we take an inverse, we take the function and we just reflect it over y equals x, correct? If we were to do that, would we get an entire parabola? If I reflect this picture about y equals x, what would we get?
Wouldn't it be the same picture, just in a different spot in the graph?
Yes. Okay, so let's talk about the inverse. Instead of -2, 0, it would be 0, -2. Instead of -1, 1, it would be 1, -1. We would have something that looks like this. What is that? Half of a parabola. We cannot have an entire parabola because it doesn't have an inverse, okay? So when we get down to the domain and range for this inverse, remember, whatever our original function is, the domain and range just switch. So the domain for our inverse is 0 to infinity, because that's the range up here. Our range is -2 to infinity, because that's the domain up there. Okay? Please look at the domain and range of your original function first before you find the domain and range of your inverse. Because in this situation, yes, we have a quadratic equation, but because we started with a square root function, we only get half of a parabola when we take the inverse. Okay? Can everybody visualize that okay? Okay, and to find the domain and range for that square root graph, easiest way to do it is just make your quick sketch because you know your transformation so well, right? Okay. Here's your homework. What else will I be looking at tomorrow?
student functions.
Your parent function.